Waves, experiment number 10, 2212 K-Lab. Learning objectives of today's presentation is to understand superposition of two sinusoidal waves moving in opposite directions, to study wave propagation in a string, to understand the formation of standing waves on a string, to understand relationships between physical parameters such as tension and length of the string, and wave features such as velocity, wavelength, and frequency for the standing waves. Also, we will discuss the relationship between the number of antinodes and frequency and tension. Today's presentation consists of 4 parts. Part A is about introduction. Part B is about the experimental setup and how that practical may be performed. Part C is related to the questions in the lab manual and their description. And last part will be related to the difficulties that may happen in performing the practical. And there are some suggestion questions which can be added in the manual or which can be asked from the students. So starting the first part, which is the introduction. We know that wave is the disturbance that travels through the medium and space. Now waves may be of any size and shape. Their speed does not depend on the size and shape. So suppose this string is vibrating. So when it's vibrating, its displacement from the mean position changes with time. The value of its distance from the mean position at any time is known as its instantaneous displacement. And the maximum value of displacement is known as amplitude, which is shown by the yellow arrow. When we talk about the sinusoidal waves, these are the periodic waves. They have a regular pattern of crest and trough. We know that crest is the pattern above the equilibrium position and the trough is the pattern below the equilibrium position. And the distance between two consecutive crests or the distance between two consecutive trough is known as the wavelength, which is represented by a Greek letter lambda. When we talk about speed of wave can be calculated from the formula V equals F lambda, where F is the frequency and lambda is the wavelength. And the units of speed will be meter per second or the distance per time. We can see from this figure that if frequency is lower, that is number of cycles per second. Frequency is defined as number of cycles per second, vibrations per second. So when the frequency is lower, wavelength is higher. But now when the frequency is higher, then the wavelength is lowered. So it means frequency and wavelength are inversely proportional to each other. Introducing the concept of principle of superposition. We were talking about a single wave in a string, but what happens when two waves combine? When two waves combine, then the resultant wave has the amplitude, which is the combination of the amplitudes of the individual waves. This is the principle of superposition. If the two waves superimpose each other in such a way that the crest of first wave falls on the crest of the other wave and the trough of first wave falls on the trough of the other wave, then the resultant wave will have the maximum amplitude and is known as the constructive interference. But what happens when the crest of first wave falls on the trough of the second wave, then they cancel the effect of each other and we have the destructive interference. This principle of superposition can be applied in understanding the concept of standing waves. Standing waves, also called the stationary waves, is the combination of two waves moving in the opposite direction. So two waves which are moving in the opposite direction, having the same amplitude and the frequency, when superimposed each other, they give a resultant wave, which is known as the standing wave. The amplitude of this standing wave is the combination of the individual component waves. In standing waves, there are the points that undergo the maximum displacement during each vibrational cycle. These points are known as the antinodes, while there are points along the standing wave where the wave has minimum amplitude. These points are known as nodes. So standing wave is the combination of nodes and antinodes. In real life, it may happen that when you vibrate a string or a chain, it's possible that you get a kind of vibration that you are generating a wave. but the wave doesn't propagate. It seems to be dancing or vibrating up and down in a place. This is actually the standing wave, example of a standing wave. So you may see that in the standing waves, you have kind of loops or the segments. We will discuss the relationship of these loops, nodes, antinodes, and wavelength. In figure 1, part A, you may see that there are two nodes and one antinode. Like the ends which are fixed, there are nodes, and in between the nodes, one antinode is formed. So first case of figure 1 has one segment, has one antinode, and two nodes. If we see the second case of the figure 1, there are two antinodes, two segments, and three nodes. And one more thing which is need to be considered is that wavelength is decreased as compared to the first one. When there was one loop, wavelength was higher. When there are two loops, wavelength has been lowered. Now last part of the figure 1, again the wavelength has been lowered. The number of loops have been increased, that is the number of segments have been increased. So there are three segments, there are three antinodes, and there are four nodes. Figure 2 represents the relationship between the wavelength, nodes, and antinodes. We see that wavelength is the distance between two consecutive crests or between two consecutive troughs. So for a wavelength, there are, for one wavelength, there are two antinodes and three nodes. We conclude that the relationship between the segments and the antinodes is that the number of segments will always be equal to the number of antinodes. The wavelength will be inversely proportional to the antinode. As from the figure 1, we see that as the wavelength is decreasing, the number of antinodes are increasing. And number of nodes are always equal to number of segments plus 1 or number to be remembered. Consider the first figure, which shows the standing waves in a stringed instrument. The first case of the figure 1 having a one loop and the length of the string is equals to L. The second case has two loops and the third case has three loops. So for the first case, when there is one loop, if you want to find out the value for the wavelength, so we see that this is 1/2 wave. This is not the complete wave. As this is 1/2 wave, so lambda wavelength will be equal to 2L. And in order to find out the frequency equals V by lambda, substituting the value of lambda 2L, the frequency for this first case when there is only one loop, the frequency will be V by 2L. In the second case, when we have two segments, for two segments, these are two half waves or one complete wave. So you may say that lambda 2 will be equal to L, that will be equal to the total length of the string, and frequency F2 will be equal to V by L. In the last case where there are three segments, lambda 3 will be equal to 2 by 3L, and F3 will be equal to 3V by 2L. So from this discussion, we can conclude, and it's clear, that as the string vibrates in more and more loops, the frequency goes on increasing and the wavelength gets correspondingly shorter. However, the product of frequency and wavelength is always equal to V. These equations also establishes that the stationary waves have a discrete set of frequencies. That is F1, 2F1, 3F1. It means that the stationary waves will not be produced or can only be set up on the string with the frequencies of the harmonic series. This is known as the harmonic series. For example, in the first case, F1 is known as the first harmonic, the second case is known as the second harmonic, and in the third case, it's known as the third harmonic. So this is the harmonic series. We have a clear relation between the frequencies and we have a clear relation between the wavelengths. Also, the speed of the wave depends on the tension in the string. We have the formula V equals under root of Ft by mu, where mu is the linear density, mass density, which is mass per unit length, and F is the tension. So we may say that speed of the wave is directly proportional to the tension. This is end of the part